Hi everyone, welcome to part 2 of the inclined plane experiment. So we still have our displacement versus time graph. I'm going to demonstrate a different way to create a mathematical model for this data. So we've got our time and our displacements with absolute uncertainties. I've plotted them, I have error bars, we're ready to go. Now the thing I want to focus on this time is the expected equation s equals a over 2 by t squared. I have values for s and for t here, but what I don't have is a value for a. So I'm just going to guess the value for a. I might put that up over here. A equals, and I'll guess the number 1. It's probably not right, but it's a start. It's just a placeholder. We'll refine that as we go. Now, I would note here that the displacement information here, these are observations. These were from our experiment. Try spelling it. And what I'd like to have here is predictions or a model. Having a hard time spelling today. Now these will still be displacement and they will still be in metres. So I'm going to use the formula s equals a over 2 multiplied by t squared, using this value for a and of course using these measured values for time. So here we go. I'll start my formula. It's the acceleration that I'm storing there, absolute reference, over 2 multiplied by time squared. Now, this is doing a dreadful job. The observation gave a displacement of 0.2. My prediction is 1.75. Nowhere near. Clearly I have to reduce that a bit. Even if I reduce that to a half, it won't be enough. Maybe reduce that to 0.2. Still not enough. Maybe reduce it to 0.1. Okay, a bit under. You can see how that number is supposed to be 0.2. I'll get an even better idea if I predict all of them. Now, what I'm going to do is plot that new set of information on my graph, because the easiest way to compare two things is visually rather than through a table. So I'll come back to my graph, go to the Design tab, add a new data series. The x values will still be those. The y values will be my predictions. You can see my predictions, these orange dots are just a little bit off. I'd rather not have them as dots. I'd rather format that to make it into a line. So a solid line, I don't mind that if it's orange, I'll make it a bit thinner. And the markers, I'll take away those orange dots, I don't want the markers there. So I've got that line and I've got my, now if I adjust this a bit, if I make that go up to 0.2, I'm way too high, so maybe 0.15, I'm still a bit too high, 0.14, not enough, 0.12 perhaps, that's looking pretty good. So this prediction is totally, I'm playing around with the acceleration value until the model, the predictions, are the best match they can be for the observations. Now there's a better way we can do this other than just visually. We can calculate the residual value. The residual is always the observed value subtract the predicted value. Now in the first case there, the observation is 0.2, the prediction is 0.211, the residual is then negative number, meaning the observation is a little bit below the prediction. If I copy those down, you can see some of them are positives and some of them are negatives. It's the job of the model is to match the graph, and to match the graph we want the residuals to be as small as possible. You might be tempted to just average the residuals, but then the positive and negative ones tend to cancel each other out, and you can get a false sense of a good fit when it's really not a good fit. What we do is we square the residuals. Squaring the residuals, that was an unfortunate turn of events. I didn't really want my table to get all messed up like that. So squaring the residuals makes them all positives. And importantly, I can now add them. So I'll do that. I'll find the sum of those residuals, 0.0038. Now that's just by me playing around here with acceleration. If I had a bad value for acceleration, like 0.2, see how the picture over here doesn't match, and you see how large the squared residual sum becomes. This is the sum of the squared residuals. Now what we're trying to do, of course, is match the picture on the graph, and a way of measuring that is by having this sum of squared residuals to be as small as possible. I could literally keep on playing here randomly, or I could use Excel's solver function. Now, solver is really tailor-made for this. I'm going to have my objective, my target cell is this one. I want it to be minimized, and how do I want it to be controlled? By changing the value of the acceleration in that cell. Make unconstrained, no, I don't like that ticked. And then we try solving, and I get a little confirmation message to say that it thinks it's worked. It's ever so, well, it looks like a good fit. It's changed the number. I started with 0.12, and it's got a smaller value here. So that's my acceleration from applying the model that I expected to the observations. If I wanted to see that orange line going backwards, I could click on the line and I could format that. Now, no, I can't do that. Sorry, because it's not a trend line. It's just going to be where it is. I'm not going to be able to send that one backwards. But I can, of course, calculate the R squared value. Calculating the R squared value is a little bit more fun. I need the total error, and I need the total error squared. Now you might say, what is the total error? Well, first thing I need to do is find the mean of the Y values. So they were my Y values. I'll find the mean of those. There it is. And the total error over here is the Y value subtract the mean of the Y values. So F4 for that, always use the mean. Now, this tells you how much variation there is in the Y values. Again, some are positive, some are negative. So we square them. All of the total errors are squared, and then we sum those. And this is the sum of the squared error. Now let me put a few more boxes here to keep things organised. And I'll put a box around that bit and a box there. Now, how do I calculate the coefficient of determination? Well, the formula goes like this. It's 1 subtract the sum of the squared residuals divided by the sum of the squared errors. My coefficient of determination for the model that I just made is 0.994. That's a pretty high value, which means that it's a good model. I still don't get an error uncertainty or an error estimate for my acceleration, but after all, this is a graph involving curved lines and curved data. So we were never really going to get much more than this out of a displacement time graph where it's a curved graph. Okay, that's enough for this video. Thanks for watching.